Hello, student. Hi, good evening. So, today we are going to see about sampling. Okay, so we are going to discuss about the topic of what sampling. Okay, sampling of the signal, sampling of sampling of analog signal. Okay, so sampling of analog signal, sampling of analog signal. Okay, so this signal is my x of t signal. Okay, so this is what topic about sampling of signal, sampling of analog signal. Okay, sampling of analog signal. So what actually how, because if you have what signal, let us say this is your voice signal. Okay, so like this is one person here. Okay, so this is one of the person. So he's what he's talking something. Okay, he's speaking to you. Okay, so he's speaking to you. Then what his voice signal, what is the frequency of that signal? Voice signal frequency is nothing but about it is approximately about, we can say, 4 kilohertz, 4 kilohertz of signal. Okay, 4 kilohertz. And this is what continuous time signal, what continuous time signal. So this is my continuous time signal. Okay, so this is my continuous time signal. So but I want to convert this signal, continuous time signal or analog signal, to a digital signal. For converting to digital signal, what we need? So we need sampling, we need what sampling, then we need quantization, then after that we need sampling, we need to apply this to sampling, then after that we need to apply this to quantizer. Okay, quantization, then after quantization we need to convert this into, then we need to encode this signal. Okay, so then after encoding we need to apply this to line coder. Okay, line coder, we need to apply to this line coder. Then this line coder will convert this your voice into bit stream like 0 1 1 0 1. Okay, so this is a process, this is one type of process. Means if you want to, if 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 some if you want to convert your voice signal into a digital signal, this is the process. First your voice signal, so that will get, first we will make it what, band limited. Okay, so through what, anti-aliasing filter. Okay, so anti-aliasing filter is applying before the sampling in order to what, in order to band limit the signal. Okay, band limited signal. So then after that we are applying the sampling. Through sampling process, today we are going to learn about sampling. Okay, so this is sampling. So it will sample the signal, means it will discretize the signal in time domain. Okay, so but it is continuous in amplitude domain. This sampling process, it will process the signal and it will convert your continuous time signal into discrete time signal, which is discrete in time but continuous in amplitude. Then after that quantization, it will quantize this sample into the nearest nearest fixed level. Okay, so this quantization process, after sampling we are applying quantization. Okay, so this quantization process is like that. It will digitize the signal. Okay, so digitize the signal means the signal is both discrete in time domain, discrete in time, as well as discrete in amplitude after quantization. Okay, so then after that this quantization level, in order to represent this quantization level, we are applying to this encoder. So encoder will fix the binary value to each level. Okay, so it will fix the binary value to each level. Then after that this encoder is applied to line coder. The line coder will give what? Line coder will give the specific, will give what, line voltage. It will give the voltage to each bit stream. Okay, so this is what actual process of what how we convert the continuous time signal to discrete and digital signal. Continuous time signal to digital signal. Okay, so this is my analog signal. Now see analog signal, how we convert this. Let's say I have message signal. Okay, I have message signal M of t. Okay, so this is my message signal, and it is band limited. Okay, so when I will take Fourier transform, let's say this is band limited to fm hertz. This is band limited to fm hertz. Okay, this is my signal that is band limited to fm hertz, f hertz. It is band limited to f hertz. Okay, so and this is my m of f, m of f. Now I want to sample this signal. Okay, because I want to what, I want to convert my message signal into what, digital signal. This is a baseband signal. First of all, I have to convert this into discrete time signal. Okay, so I want to discretize this. Okay, so over I want to discretize this signal. Okay, so this is what band limited to fm hertz, fm hertz minus fm plus fm. Okay, so this is my message signal, message signal. So now what I will do here, if you see, first of all, this is my m of t signal, m of t. So just first you just multiply this signal with what, with impulse train. What impulse train? You take one impulse train. This is my impulse train. Okay, so this is what impulse train, which is periodic impulse train. I have one periodic impulse train, that is p of t, p of t. Okay, with amplitude 1, p of t. So this is 0 ts, 2 ts, 3 ts, 4 ts. Yes, 4 ts. So this is my nt. This is my impulse train. This is my impulse train. Okay, so impulse train. So this impulse train is nothing but p of t is equal to what? P of t is equal to summation n is equal to minus infinite to plus infinite. Plus infinite delta of t minus nt. T minus nt. Okay, nts. So this is what impulse train. So I want to convert this message signal. Our main target is what, to convert this message signal to discrete time signal. Okay, so this message signal is continuous in time domain. Okay, so this is what continuous in time domain. This message signal continuous in time domain. Okay, so we just want to sample it. We just want to sample it. So this is for sampling. What is the sampling way? Sampling, to how to sample this signal, just multiply it with this impulse train, this impulse train. Then I will get what? I will get sampled message signal. Sampled message signal. This sampled message signal is what? See here, this sampled message signal is nothing but, it is what, m of t, m of t into what, m of t into p of t, m of t into p of t. Okay, so then after that, what you just do, m of t into p of t is what, this summation n is equal to minus infinite to plus infinite. So this is delta of t minus nt, t minus nt. So this is what, this I have multiplied. This is my sampling process. Okay, sampling process. So we want to sample it. Now we have sampled this signal. Okay, so this is my now how it will come. So just we will see this in frequency domain. Okay, you can do also in time domain, but we will see it through frequency domain properly. Okay, so why? Because why we are doing frequency, why we are doing it's, why we want to see this in frequency domain, because in frequency domain we can see properly this signal. Okay, so because some of the information that is inherent, that is hidden in the time domain, that we are unable to see properly in time domain. That's why we are doing Fourier transform, so that we can see its spectrum properly, how actually this, how actually what is the actual information that is hidden inside the message signal in time domain. Okay, for that we need what, we need to convert this into frequency domain. Okay, so this is my m of t into what, p of t. So this is what sampling process, we are just doing this sampling process. Okay, so then after sampling process, you know very well, if there is what, multiplication in time domain, multiplication in time domain correspond to convolution in frequency domain. Okay, convolution in frequency domain. So then here I can write, this is my message signal. Okay, message signal, sampled message signal is equal to, sampled message signal is equal to what, is equal to this m of t. So just apply what Fourier transform to this signal. Okay, when we apply the Fourier transform, then this is my message signal in frequency domain. ms of f ms of f is equal to what? Is equal to m of f in frequency domain convolution, because we know multiplication in time domain correspond to convolution in frequency domain. So this is what n is equal to minus infinite to plus infinite. So this is what this is my I am doing here Fourier transform of this. Okay, convolution. Better to write like this: convolution of p of f. Okay, p of f. So then I will give the proper explanation for this p of f, because it is what periodic signal, periodic signal. For periodic signal, we have to take the Fourier series expression. Then after that we will apply the Fourier transform. So this is my expression for sampling of signal in frequency domain. Okay, so this is in time domain. So now see, frequency domain, time domain. Now up to this, now we are confirmed. Okay, so what we have done. So now see what is p of f, because what impulse train directly we cannot take the Fourier transform. First of all we have to take the Fourier series, because it is a periodic signal. So p of t, what p of t is, nothing but n is equal to minus infinite to plus infinite, delta of t minus nt, yes, this is what periodic signal. Yes or no? Periodic signal. So that's why first of all take the Fourier series of this. Let's say this Fourier series is ps of t is equal to what? Summation n is equal to minus infinite to plus infinite. Okay, plus infinite. If you then this is plus infinite into cn e to the power j n omega naught t, So what is cn? Cn is the Fourier series coefficient. What is cn? Here cn is nothing but Fourier series coefficient. Fourier series coefficient. This is Fourier series coefficient. Okay, so this is my Fourier series coefficient cn. Okay, so now here we want to calculate this Fourier series coefficient. What is this? Cn is equal to what? 1 by time period. Okay, so this is my periodic signal. See, periodic signal. So this is periodic signal. Periodic. Okay, up to infinite time. So this is t, this is 2t, this is 3t, and so on. So this is my p of t. So c of n is equal to 1 by t, integration 0 to t p of t into e to the power minus jn omega naught t dt. Okay, so this is what? This is Fourier series coefficient. Okay, so that I want to calculate. So this is what? 1 by t integration 1 by t integration. Now what I will do here, just take, this is my time period t. Okay, time period t, just take t by 2 minus t by 2 to plus t by 2, which contain one sample within this period. Okay, so that's why what I will do here, minus t by 2 to plus t by 2 plus t by 2. What is plus t by 2? What is this duration containing? This is about this duration. Okay, this duration, because time period is t. Okay, so then I can divide this up to this minus t by 2 to plus t by 2. It is containing only this single what? Single impulse. That is what? That is nothing but delta of t. Then I can write here delta of t into e to the power minus j n omega naught t dt. Jn omega naught t dt. So see here, cn is equal to 1 by t. Cn is equal to 1 by t integration minus t by 2 to plus t by 2 delta of t into e to the power jn omega naught t. Here what we will apply? Sampling property. So it will come delta of t into dt. So what is this sampling property? So this is what? Cn is equal to 1 by t delta t. Now see here. This is up to this. Okay, so now I will tell sampling property. So what is the sampling property? That we know very well, that is nothing but if x of t into delta of t, plus minus and t naught. Okay, so plus minus t naught, plus minus plus minus t naught is nothing but equal to x of this is plus minus t naught, plus minus t naught. So x of t is nothing but minus plus t naught into delta of t plus minus t naught. This is my sampling property. Okay, this is my sampling property. So that's why we have to put that sampling property into Fourier series coefficient. Fourier series coefficient Cn is equal to 1 by t integration minus t by 2 to t by 2 to t by 2. Okay, so this is delta of t into e to the power minus j and omega naught t delta of omega naught t dt. Okay, so this is nothing but if you will apply that sampling property. Okay, sampling property, what is t naught here? 0. So this is what 0 means, it is delta of t minus 0 na, t minus 0. We have to put here 0. Okay, why? Because we are applying sampling property. So this is delta of t into e to the power j n 0 dt, j n 0 dt. Okay, so this is 1 by t here, and this is t by 2 minus t by 2, and this is t by 2. So after applying sampling property, so what we get here, cn is equal to what? 1 by t. Cn is equal to 1 by t integration 0 to integration minus t by 2 to minus t by 2 to plus t by 2 delta of t dt. So Cn is equal to 1 by t integration minus t by 2 to plus t by 2 delta of t is equal to what? Is equal to area under impulse is nothing but 1. Yes, area under impulse is always unity, 1. Okay, so therefore what we got? Cn. So this is what Fourier series coefficient. Now Fourier series coefficient we got what? 1 by t. So that only I want to make you understand this what, because I can write directly, because I want to reveal properly to you so how it came. Okay, so that's why where we are. So see here, we are m, we are at this point m. So m, this is what, and delta of t, it is nothing but, this is nothing but what? Sampling of massive signal. So which is nothing but m of t into summation n is equal to minus infinite to plus infinite delta of t minus n t and t. Okay, and t. Now we are going to what? Taking Fourier transform for this. Okay, so this is what m delta of f is equal to what? Is equal to m of f. See here, multiplication in time domain correspond to convolution in frequency domain. So this is n is equal to minus infinite to plus infinite. Okay, plus infinite. Okay, now see we have seen what? We have seen the Fourier transform for this. No, we have seen what? We have seen, just wait. So just after that we will apply. So just you see this m delta of t is equal to m of t. What is the Fourier series that we have calculated? Is nothing but 1 by t integration 1 by t summation. This is what Fourier series expression for this. Okay, so just now we have calculated 1 by t summation n equal to minus infinite to plus infinite. This is delta of t minus, no, so this is what? This is the value of Cn. Okay, this is the value of Cn. Okay, Cn, and it is e to the power j and omega naught t, j and omega naught t. Okay, so understood? Have you understood this? So this is m of t into this is what? Actually it is a periodic signal, periodic impulse train in the sense we have to find the Fourier series that we have calculated. Okay, so what is the Fourier series for this? Fourier series is 1 by t integrate 1 by t summation n is equal to minus infinite to plus infinite e to the power gn omega naught t. So this is what? So this is the Fourier series. Okay, so now we can take, now we are eligible and we are what, we can take the Fourier transform now. Okay, so this actually I want to make you understand. So first of all, we have to take the Fourier series, then after that we have to take the Fourier transform. Okay, so otherwise directly I can write, but someone cannot understand directly if I will do. Okay, so this is the process. Now you can write. Now we can apply Fourier transform. By applying Fourier transform, what we will get here, m delta of f is equal to m of f, m of f. Okay, multiplication in time domain, convolution in frequency domain. 1 by t, so 1 by t, just take here 1 by t, 1 by t, summation n is equal to minus infinite to plus infinite. What is the Fourier transform of this? Is nothing but delta of f minus nf naught. Okay, nf naught, f naught is equal to what, 1 by t, 1 by t. Okay, 1 by t. T is what, sampling interval. T is what, sampling interval. So now just do this. M delta of f is equal to what, m delta of f is nothing but just, this is what, 1 by t, 1 by t, 1 by t, summation n is equal to minus infinite to plus infinite. Okay, m of f convolution delta of f minus nf naught. Okay, so this is my nf naught. F naught here actually it is a sampling frequency, fs. F naught is nothing but here fs. Okay, fs. So I can write this fs omega s. Okay, sampling frequency, we are sampling the signal. Okay, so this is, now here I will apply convolution property. M of f convolution delta of f minus nfs. So now see, up to this is okay. So nothing we have done. So first we have applied the Fourier series here because it is a periodic signal. Okay, so first of all we have to express any periodic signal in the form of Fourier series. After that we have to take the Fourier transform. Okay, in order to convert this signal into a frequency domain. Okay, why? Because frequency domain we are able to see the signal properly. Whatever some amount of information that is hidden inside the time domain signal, so where we are unable to see properly. So that's why we are taking the Fourier transform. Okay, so that is the main purpose of taking the Fourier transform. Some information is hidden inside the time domain signal that we are unable to observe properly. So for that we are taking the Fourier transform. Okay, so we are taking the Fourier transform, and in frequency domain we are able to see the properly see the proper information. Okay, so information that is contained within the signal. Okay, so that is the main purpose of why we are going to Fourier transform. Okay, so now we can apply, after applying this Fourier series, now we can apply the Fourier transform. Okay, so Fourier transform, in Fourier transform, as you know, this is multiplication, this is convolution. Multiplication in time domain correspond to convolution in frequency domain. Okay, so now see, so up to this is okay. So now I'm going to rub this. So let's see, this is actually what, this is the process of what, process of sampling. We are sampling the continuous time signal. So now we have reached up to this one. Okay, so this is what, m delta of f, this is a sampled signal in frequency domain, m delta of f. Okay, m delta of f, this is what, 1 by t, summation n is equal to minus infinite plus infinite, and this is what, plus infinite. Okay, so and this is what here, m of f convolution delta of f minus nfs. Okay, f minus nfs. Okay, this is my sampling frequency. Here I am going to apply what, I am going to apply the convolution property. Convolution property is what, x of f convolution delta of f minus f naught is equal to x of f naught into x of f naught. So this is my convolution property. Okay, x of f convolution delta of f minus f naught is nothing but x of f naught. This is my convolution property. Now this convolution property we are going to apply in this. Okay, in this expression. Okay, in this expression, now see here, m delta of f is equal to 1 by t, summation n is equal to minus infinite to plus infinite. Okay, so what is convolution property? This m of this will come as it is n into fs, n into fs. Okay, so n into convolution. Okay, sorry. So convolution property. So that is sampling property. Sorry. So there is one point. So I have missed one point. So this is nothing but x of f convolution delta of f minus n f minus f naught is equal to x of f minus f naught. This is actually the convolution property, not that. Okay, so just now I have told you that is wrong. Okay, so that is a sampling frequency, that is a sampling property. Okay, so this is my convolution property, x of f convolution delta of f minus f naught is equal to x of f minus f naught. Okay, now we are going to apply this property into this expression. Okay, so now see, just small mistake that I came with small mistake. Okay, so just avoid it. So now see here, now see, by applying the convolution property, what I will get, m delta of f is equal to 1 by t summation n is equal to minus infinite to plus infinite m of what, f minus and f naught. Okay, so this is what my final expression of what, my final expression of sampling signal. Okay, my final expression of sampling my final expression of sampling is what, this one. Okay, so this is my sampling of what, sampling of continuous time domain signal. Okay, so in frequency domain. Okay, so now we are going to map it. Okay, we are going to show the spectrum of this signal that we have got. Okay, so this is my message signal in the form of what, in the message signal. Okay, so this is my message signal. Just by putting the value of n, we can generate the replica of the original signal. So now see this one expression, by putting the value of n, we can replicate this message signal. Okay, so message signal, now see here. So for that, as we have got what, as we have got m delta of f. Okay, so this is my sampling of message signal in the frequency domain. In that we got what, 1 by t summation n is equal to minus infinite to plus infinite m of f minus and fs. Okay, f minus and fs, where my message signal, that is a baseband signal, is band limited to what, fm. It is band limited to fm, that we have seen. Okay, so this is band limited to fm. So now see here, band limited to fm. Now if I want to what, if I want to recover this message signal. Okay, if I want to, because they are according to sampling. Okay, so we have to sample the signal in such a way that at the receiver side I am able to recover this message signal properly from its sample signal. For that we have to apply what, Nyquist theorem. Okay, so Nyquist theorem. So for sampling, Nyquist theorem means, this is what, Nyquist theorem. Okay, so Nyquist theorem, just mathematically I am saying this. Nyquist theorem is what, Nyquist theorem state that the sampling frequency should be equal to twice the bandwidth of message signal. If the sampling frequency is exactly twice the bandwidth of message signal, in that case what happens? In that case we are able to recover our original signal from its sampled version at the reception side. Okay, so we are, if the message signal is band limited to fm hertz. Okay, fm hertz, after sampling at the receiver side we are able to recover our original message signal from its sample, if the sampling is if and only if the sampling is done at least at the rate of twice of its bandwidth, twice of its baseband signal. Okay, so then in that case we can say that we are able to recover over message signal properly. Okay, so see this spectrum for this spectrum is what spectrum will be like this. So this is spectrum for this. Okay, so this is my this is my original signal. Okay, and this is my replica of this original signal, replica of original signal that we have sampled. Okay, so this is my original signal replica. Okay, so now this is what, this is fs, and this is my 2fs, and this is my 3fs, this is my 3fs, and so on. This is my minus fs, this is my minus 2fs, and this is what amplitude is nothing but 1 by t, and this is my m delta of f. Okay, so this is my message sampled message signal in frequency domain. Okay, frequency domain where god band, this is my god band is how much? 0 hertz. god band is 0 hertz. Okay, so see here, this is at receiver side. After applying the low pass filter with cutoff frequency, this is my fm, this is my minus fm. Okay, after applying this sample message signal to the low pass filter of cutoff frequency fm, and we are able to recover over original message signal, okay, original message signal fm. Okay, this is happening at receiver side. Okay, at receiver side I am able to recover my original signal from its sample. Okay, from its sample, which is this is what critical sampling, fs is equal to 2fm, okay, this is my critical sample. And this is what, this is nothing but here god band means, so this is god band means separation between the adjacent signal. Okay, adjacent signal, the separation between the original signal and its replica is 0, indicating that god band is 0. God band 0 means there is no separation, and there is also no loss of information also, means it is exact sampling of the message signal. From here we are able to recover the original signal, after passing through the low pass filter, which is possible only the at nyquist state. At nyquist state means we are sampling over message signal just twice of its bandwidth, then it is possible to recover the original message signal. So this is whole of the history what we have done. First we have taken one message signal. Okay, after that is we have taken our voice signal as a message signal. Then after that we just multiplied that signal with the periodic impulse stream. Okay, so then after that we got the discretized signal from continuous time signal. Okay, so then after that, because as we know very well, the whatever the information we are able to see in the time domain, so there is some information that is hidden within the signal. So that's why we have to go for frequency domain signal. Okay, so for frequency domain we have to apply the Fourier transform. But the impulse train that we have seen here, that is periodic impulse train, that is a periodic impulse train. First of all, we have to take the Fourier series of that periodic impulse train, and then after that we have to apply the Fourier transform. Okay, Fourier transform. Then after applying the Fourier transform, we got this what sampled message signal in frequency domain. Okay, so then we are able to see. Okay, so when we sample this message signal exactly at the Nyquist state, then what information that we can get is that we are able to recover original signal from its sample at the receiver side. Okay, so without any loss of information. This is all about simple expression forward sampling theorem. Okay, so sampling theorem. Today we have learned about total sampling theorem. What is sampling theorem? Why we need sampling theorem? Sampling theorem, just we need to discretize the signal. Okay, discretize what signal, which is time domain, and we want to convert this into a discrete time signal. Okay, so then after sampling we have to go for what quantization process. Then after that we have to go for encoder, then line coder. Okay, after all this process we are able to convert over analog signal to into digital signal. Okay, so this is the first part of this process. this sampling process is a first part of the process of digital signal. Okay, so that's all for today about this sampling of the continuous time signal. So thank you very much. Okay, thank you.